Okay, welcome back to Algebra 2. Take 2 of this video. I forgot to record the first one, apparently. So I'm redoing this. You live, you learn, I guess. This is Algebra 2. We are currently at the point where we are in roots and radicals, learning how to put them in the same order and the same index, learning how to multiply and division. That's what we're talking about today. The original video that I did was like 40 minutes long because I did a multiplication and division tutorial. I think I'm going to split it up. This way, if I make mistakes, it's not all lost work. I'm also going to try to quit saying which seems to be difficult for me. If you are in my class, this would be work on page 198 and 199. And we're just going to go ahead and jump right into it, but I'm going to check to make sure I am recording. And it looks like we're good. So, all of the rules that we've learned so far for radicals are applied thus far in everything else we learn. That's how math is. It's like a building subject. Once you learn something way back in first grade, you can plan on doing it for the rest of every year that you have math. The new thing here is just to make sure that we reduce the radicals to the same order. The same order is the index number, the little cube in this case, and this one's a square because there's no number here. They have to be the same in order to multiply or divide. You also want to reduce as much as you can bigger numbers like this to make it easier to work with. So hopefully second time's a charm here. I've already done this once. I don't particularly want to do it again. It is not my favorite thing, but we'll do it anyways. So these start off just like any other math class, or at least any of the ones that we have here, with easier problems and they get difficult. So I have a wide array of stuff on the board that hopefully will cover just about everything that you run into. Of course, there's going to be 1 or 2 problems that fit a bunch of different categories and not exactly like these, but the skills that you get from these should be able to help you with those. Do your best, try, and follow along with me, and hopefully that will help you. So number 1 here is very simple. This is a square root. Again, we do not write the square. It's just understood because that's a square root symbol. So they are already in the same order. So I don't have to do anything there. All I'm going to do is actually multiply these. 12 times 3, which results in 36 under the radical. Now that is the square root of 36. If you can simplify, you must simplify. Well, there is a perfect square of 36, and that is 6. So obviously it's that easy, and they're not going to give you too many like that. So take them while you can. 6 is similar, that it has the same order already. They're both cube roots, so that's great. But it has numbers on the outside and numbers on the inside. So I picked that one to show you that whatever you do on the outside doesn't really affect what you do on the inside. You still need to multiply the outside. 2 times 2, which is going to give me a 4. Okay, then you're going to go ahead and multiply the inside. 9 times 15, I think, is 135 because I just did this problem, but I will double check just to make sure. Yes, it is 135. Don't ask me why my radical is so long right here. I'm not sure. However, we can break that down. I'm almost positive that 135 is not the smallest root under there. Do not forget your cube like I just did out there, because then you're going to think it's a square root. Don't do that. Since this is a cube root, I'm going to go ahead and list some of the cubes so that I can divide into this to see if I can break it down. So you don't have to go very far. Because they go up pretty fast. 2 cubed is 8, 3 cubed is 27. All I'm doing is 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, 5 times 5 times 5, or you can use your cube button on your calculator. 4 cubed is 64, and 5 cubed is 125. So then I'm going to take these numbers and divide them in to see if any go in evenly. And they do. 27 times 5 makes up 135. So I break that down. This is how we reduce radicals. There is a cube root of 27. If I look over here, it's 3. So if I pull that 3 out, it's got to come to the outside. When it comes to the outside, it multiplies. So this is 4 times 3. That is going to give me a 12. And this 5, because I couldn't take it out, stays in the radical. And this is my answer, fully reduced. Okay? So those main basic skills is what you're going to use on all of these. They're just not all that simple. They like to throw, just like the geometry video I just did, even though we were doing area of a bunch of different shapes and polygons, we kept having to use the Pythagorean theorem, which was nothing to do with what we were doing, but they're not just going to give you all easy problems. You got to use your head, use your skills. All right, so number 9 is our first instance, not necessarily on this page, but the first one that I'm going to do with you that we don't match. There's a 3 and this one's a square root. They're not the same, okay? Now, what you would want to try to do first, you can kind of go about it 2 different ways. You could go ahead and try to make those a 6, and I'll show you that in a minute. But to get them in the same index, you want the numbers to match. So if this one is a square root and that's a 3, a 2 and a 3, the first number is a 6. And you would go ahead and put them in fractional exponent form. But before I do that, I'm going to see if I can get a cube out of this to simplify it so that I don't have to work with such a big number. All right. So if I go look at the cubes that I just wrote up here, I know 125 is going to go into that, all right, because it's half of that. So I could break this down to 125 times 2, okay? There is a cube root of 125. It's 5, okay? That 5 comes out here and gets multiplied. So that makes that 10. And the cube root, and what's left in here is just 2. So now my problem actually looks like this, okay? This is sad handwriting, okay? Shame on me. Write yours a lot better than that. Now they're still not in the same order. However, this is much easier to work with. When you put them in fractional exponents, okay, the number that's on the outside goes on the bottom, and the number that's on the inside, the exponent, these are ones. We don't write them, but they're always there to the first power. So when we write this one, ignore this 10 for now. This would be 2 1/3. When I write this one, it's going to be 2 1/2 because this is an understood 2 out there. We don't write it, but you can. It's not going to be wrong. Okay, when we look at that, you know, if you add or subtract fractions, they have to have the same denominators. And when we multiply things with exponents, you add them, so therefore they need the same. So we need to make those both 6s because 3 and 2 both go into 6. What do I multiply 3 by? Well, it's a 2. Whatever I do on the top or the bottom, I have to do to the top. This one was a 2. I need to multiply by 3. So when I do that, if you look over here, this one's going to end up being 2 2/6. And I don't know why I wrote it giant like that. It's an exponent, not a mixed number. So 2 2/6. And then this one is going to be 2 3/6. All right. Then we need to put them back in radical form. Okay, so what we're going to do is the top number is going to go on the inside and that bottom number is going to go on the outside. So this problem is now going to, remember this 10, is now going to be a 6 on the outside, and this will be 2 squared. This one, there was no number on the outside, but this is going to be a 6th root, and this is going to be 2 to the 3rd. Okay, we need to go ahead, order of operations says we have to apply those exponents first. So 2 times 2, this is actually 10 the 6th root of 4, and this is the 6th root of 2 cubed, which is 8. Okay, now they're the same. That was a lot of work to do that. Now we can multiply. This number on the outside gets multiplied by the number out here, which is a 1 that we don't write. 1 times 10 is 10. They are in the 6th root. 8 times 4 is 32, okay? Is there anything in there that's going to be a 6th root that I can take out? Probably not. Matter of fact, I believe 2 to the 6th power is 64, so it's already too big. This is simplified. We leave it alone. Okay? So yes, they get a little harder. A little bit more work's got to go into it. You just have to keep following the rules and keep doing. I'm going to erase this so that I can address problem 11 here. Checking to make sure we're still recording. I don't want to go through that again. All right. I picked problem 11 because it has a lot of letters in it. Of course, algebra has letters in it. That's what's different between it and regular math and arithmetic. They are not in the same root, and they have letters in it. Letters are kind of just easier than numbers because you don't have to worry about doing mathematical computations, I guess, to them. So we're going to go ahead and put them, there's nothing we can do, they're letters, so I can't take any cube roots or anything out. None of them are multiples of 3. This one is, so I could, but this is a square root, so I could simplify that down first, or I could go ahead and put them in fractional form and make them match. I'll just do the way that I just did it. So on this one, again, if I put them in fractional form, this number right here goes on the bottom, and the exponent attached to each one goes on the top. Okay? Forget about this outside 3. We don't need it until we put them back in the radicals. This would be a to the 1/2, b to the 4/2, and c to 2/2, okay? Because that's a 2 right there, all right? That's where I got those from. Now we need to make them match. Of course, we're going to make them match to 6 because 3 and 2, which will be the most of the ones that you deal with here, that's the first number that they go to. So again, this is a 3. I need to multiply it by 2. If I do that on the bottom, I must do it on the top. So this one becomes 4/6, 4/6, and that would be, whoops, I gotta write the C first, 8/6, okay? This one needs to be multiplied by 3 to make 6, so I have to do that on the top. So this is 3/6. This one will be 12/6. I don't know why I'm writing the letter so small and the exponent's so big, but those are exponents, guys. All right, and then this one would be 6/6. Okay, if I would have went ahead and reduced that, these numbers would have been different. I could have made this a 2 and that a 1. I chose not to do that yet. I can reduce them in a minute. Now I'm going to put them back in radicals, and then we are going to go ahead and multiply them and take the roots. So now these are 6 roots. So this first one, this is going to be a to the 4th, b to the 4th, c to the 8th. This 3 is still out there, it didn't go anywhere. This will be a3, b12, c6. If I would have reduced this one already, these numbers wouldn't be so high and we wouldn't be working with such a high number. It's going to work out the same way. It's your choice on how you do it. 32 is kind of in my way right here, so I'm going to go ahead and move it out of the way and just rewrite it in a minute. Don't let me forget 32. Not that you're here to remind me, but all right. When we multiply things with exponents, we add the exponents. There's nothing out here. There's a 1. 1 times 3. This is a 3. That's still a 6th root. Now 4 plus 3 is 7, so this is a to the 7th. 4 plus 12 is 16, so this is b to the 16. And 8 plus 6 is c to the 14th, okay? That is not reduced. You're going to say, well, how do I take a 6th root of a letter? It's the exponent number, okay? Whatever is out here needs to divide into that, and you need to break them down into multiples of that number. Since this is a 6, I need these to be 6s or 12s or 18s or 24s or something like that. So what I do is break them apart. A to the first and A to the 6th. If I add those, I get the 7 there, okay? On this one, I would have B to the 12th, because that's divisible by 6, and B to the 4th. And then this one, I will have C to the 12th and C squared. Because if I add them, I get 14. If I add those, I get 16. But I have one of each that is divisible by the 6th, okay? So when I pull A to the 6th out, the 6th root of A to the 6th is A. It's going to go out here with my 3. That's gone, okay? When I pull out this one, 12 divided by 6 is 2. So a B squared comes out. That one's gone. And then with this one, the 14th, 12 is again divisible by 2, or by 6, which is 2, so a C squared comes out, and that one's gone. Whatever's left stays in the radical. So this is an A to the first. You don't need to write the first up there. You can, it's not wrong, we just don't write it. B to the 4th, and C squared. 6 cannot go into any of those. They're too small. But if you have a number that's 6 or above, it can on exponents, the way that it works. So this is your final correct answer. Okay? That is helpful because pretty much everything else is going to have letters in it on this. So then you got to combine this and that. A lot of work. Okay? 2 more problems and we'll be done with this lesson, and then we'll do the division lesson. All right. So I picked this one because it has 3 and it has fractions and it looks kind of weird. However, they are all in the same root. You get one of these that doesn't have the same root, which you will, then you got to put them in the same root. But for now, when it's like this, you're going to multiply straight across the top, multiply straight across the bottom, then reduce. So let me make me a big radical here. 1 times 7 is 7. 7 times 4 is 28. 2 times 2 is 4. 4 times 5 is 20. Okay? If I reduce 28 over 20, 4 goes into both of those. And 4 goes into 28 7 times. 4 goes into 25 times. You would hope that you were done at this point and that was a simple problem, just reducing fractions. You're not done. There is a rule in radicals and roots that you can have a radical on the bottom of a fraction. It has to come out. And this big one, whether it's written like that or this, they're both the same thing. You cannot have a radical. Just like you can't have a fraction on the bottom of a fraction, you can't have a radical there either. So you have to get rid of that, which we learned when we did the addition and subtraction part. This is a square root, so we want to make this a perfect square so we can pull it out. We are going to multiply by radical 5 over radical 5. The reason we do that is because 5 times 5 is going to make 25, which is a perfect square. If you multiply something with it over itself, it's like multiplying over 1 because that reduces to 1, so you're not changing the actual problem. What we will get here on top will be radical 35. What we get on bottom is radical 25. Is there a square root of 25? Yes, it comes out. This can be written 2 ways. Radical 35 over 5, because the square root of 25 is 5. Or 1 radical 35, or 1/5 radical 35. Both of these are the same exact answer. 35, 7, and 5 are prime, so it's not going to reduce. That's okay to have a radical in the top. It's not okay to have it in the bottom. Okay? All right, I'm going to clear this off. One more problem that requires foiling. And I find it easier than these most of the time. And then we'll conclude this video and move to the next. Gotta get it real good and dry so that it doesn't smear. Alright, so the last problem I was going to show you was problem 32. Problem 32 looks like this. Okay, it is a binomial squared. That means one term here, one term here. Binomial means two terms, which means you have to FOIL, okay? Which is something we learned in Algebra 1. We need to expand this parentheses, which just means to write the problem out completely. Okay, this squared is just saying this times itself, okay? And then when we FOIL, I'll use a different color here so that you can see. The F stands for first, which means I have to multiply this, the first one and this, by the first one and that. On the outside, I have 3 times 3, which makes 9, A times A, which makes A squared. Then I have radical B times radical B, which makes radical B squared. And we will be able to simplify that, but we're not going to yet. Okay, that's the first. On the outside, I take my outer, which would be this one and this one. This is a positive because there's no sign here, and that's a negative, so our sign will be a negative. There's nothing on the outside, so that's a 1 times 3A, so this has to be 3A. And then radical B times radical A is just radical AB, and we write them alphabetically. The next one is the I, which is the inside, and it's what's on the inner part of the bracket, so it's this and this. Again, this is 3A times a 1, and it's negative because that's a negative sign. I don't know why I wrote a 1. 1 times 3 is 3, not 1, guys. All right, and then the A comes along because there's nothing else to multiply it with. And then we have radical A and radical B, which is going to give us radical AB. And then our L stands for last, which is this one and this one. A negative times a negative makes a positive. Radical A times radical A makes radical A squared, which we will simplify. All right, once we got this done, if you got that done, kudos to you. I don't necessarily count it wrong once you get this far, but generally speaking, you need to reduce these and combine the middle terms. 90% of the time when you're FOILing, the middle terms will combine together. So in this case, we don't do anything with 9A squared, but B squared, the square root of B squared is just B, so that comes along. All right, I have negative 3A minus 3A, which gives me negative 6A. Okay, that radical AB comes along like that was an X or something. You don't do anything when you're adding and subtracting. They stay the same, just like if you were adding and subtracting things with common denominators. You don't add the bottoms, their denominators stay the same. The reason why we put this in alphabetical order, if I did this one the way that it read, this would said BA. You wouldn't think that AB and BA were the same, and that would mess you up. So that's why we put them in alphabetical order. And lastly, the square root of A squared is just A. So this, a trinomial, 1, 2, 3 terms, is our answer. That concludes our lesson. Have a blessed day. I'll see you on the next one.